for the minute time, I'll leave the mic to my colleague, Dr. Tahseen, to give a quick overview of how the session will go. Thank you.
Thanks very much, Dr. Yusuf. First of all, welcome everyone. And now we reached to this very nice and interesting moment of the hackathon, where we are going to present our final work, but also feel the experience and the enjoyment of the hackathon. So the judgment criteria, every team will take about 8 minutes to present. Please don't exceed it, because there will be a timer, and also they will cut off your presentation if you exceed the 8 minutes. Then we'll have a couple of questions after from the jury members. I will moderate this session, so for the time efficiency. And then the jury member will have about 20 seconds to fill in the form that has been distributed on the group. Did everyone from the jury members get the form open already? The Google form with 5 questions. Yes, you can do it. Yeah, just only if you can submit it. And then the form will have the team number and then the jury member name. And then we have 5 questions. And the criteria will be about the creativity in quantum computing and the technical implementation, time management, confidence, judge interaction, teamwork, clear problem solution flow, demonstration of research depth, and the presentation best practices. So good luck, everyone. And we are going to now start with the first presentation, please. So we call the first team to step forward. Yes. So this is team number 1, right? Oh yeah, okay. Team number 1. Okay. Everyone is ready? Your team is ready? Are you 3 only? Okay, the rest of team 1, please step forward. We don't have much time. Okay, then present, and then we are going to make a note on your colleagues that they are not here. Okay, please start. Now start the counter, please.
Hello, everyone. Let me introduce our team. I'm Bassy Ziad. Moment. Okay. Okay.
Yes, 8 minutes. Yes. Yeah. Please follow the advice carefully. Please reset the counter. And for everyone, please follow this advice. For Dr. Ahmed, budget your time and the plan. Don't speak slowly. Just think. Get your sources straight. Okay, start the counter, please. Okay, go ahead.
Okay. I want to, before I begin, there is a sentence that is on my mind. Numbers are not just the minutes are not just numbers. There is leaves. But I want descriptions, provisions, and the problem statements. The figure out a problem, major global operation challenges with market and emergency scenarios, ambulance routing for patient transportations in Egypt, and special tasks transport 5 patients to a central hospital using 1 ambulance with maximum capacity of 3 patients per trip. Okay. Our primary objective, I want to determine routing strategy to maximize travel distance with satisfying capacity constraints. Next. Okay, I want to describe the key constraints each trip. Okay, how to describe the emergency patients transportation, hospital, central destination, and the patient's 5 DT or GR as it is, ambulance capacity, three patients per trip, and challenges multiple trips required, and Google minimize the total kilometer traveled. Next. I want to describe the key constraints. Each trip capacity less than 3 or equal. 3 patients, all patients must be assigned and transportations. And now, Engineer Ines, you will talk the next step.
So instead of relying on the collision coordinates, we obtain the real world from the open source routing machine API, which show real world map and the route directions. So this gives us the distance matrix as shown in the slide.
Whoa.
Okay. As shown in what? Yes, as shown in the slide here, that this matrix reflects the actual route network between the hospital and the patient, and also the distances between the patients themselves. So a key feature here is that the distances are directed, meaning that the route from the hospital to the patient can differ from the trip route, from the return trip can I'm sorry. The route from the hospital to the patient can differ from the return trip due to the route layout in the map. So this realistic distances matrix, this realistic distance matrix forms the basis of our optimization model, where we minimize the total travel distance through the ambulance trips, while respecting the trip capacity constraint of three patients per trip. And so to solve this problem, we obtained two approaches: the classical approach and the quantum approach. For the classical approach, we will our friend Shaima will present.
The classical approach, we kept the same pre-processing. We calculated the distance from GPS points, grouped patients by the three capacity rule, then used the brute force optimizer. This optimizer tries every possible route, calculates travel distance, then picks the one with the lowest distance for 5 patients. For 5 patients is 5, because you can check all combinations and guarantee the best solution. But at the number of patients growth, the possibilities explode. 10 patients already means millions of options. That's why it becomes what we call an NP-hard problem. And there are smarter classical methods to handle this, but we used brute force as the simple baseline and as a motivation to move to the quantum part.
Yeah, okay. So basically, we started like to formulate our problem into a cube formulation. Like it's kind of unconstrained binary. It depends. Like if we're choosing this binary variable, it's gonna be like a 1, and if it's not be selected, it's gonna be like a 0. And we're just working on the constraints. We have 2 constraints. Basically, we're making sure that every and each patient is being selected just one time in the trip, and the second constraint, the capacity of the ambulance. And we have actually worked on 2 approaches. The first one, the annealing approach, and we're just finding the least amount of energy through the quantum methodology, and then computing the best route through the classical model. And the second approach, basically, we choose the like the unconstrained binary solution ones, and like for example, like it's just both like Hamiltonian, and then the mixture operation. They together formulate our solution, and we worked on Copilot basically, and
like at the beginning, we started with a 30, only 30 constraint variables, and could reduce it to be 14. And like comparing here, the results we got here in the simulation solution, it's 58. And we tried to run like on the hardware, actual hardware, we got a 67. Like it's not really that good, but it's a bit faster, specifically like at a really high inputs or some. Like at some point, the quantum would be really beneficial. Like the classical ones wouldn't really deal with that amount of complexity. And yeah, and we just used the IBM device. It could really like we tried to calculate the like the error, and we're trying to look forward to see how to reduce that. And basically next, yeah. So basically here the comparison between the approach that we have tried. Like yeah, you would say like the difference is not really feasible here. We're having here the hardware and the annealer, the simulation, and the hardware, the actual hardware. The D-Wave solar that we have tried, we tried to run it on actual physical computer, but we couldn't really find the actual setup for that. Next slide, please. Yeah, and basically this is gonna just be helpful in the real world problem, finding the best routing just as fast as we can. As I mentioned before, we're just working on finding the solution efficiently in a
time
really
out.
manner.
We have already increased the 30 seconds for you for the disturbance. Okay, time out
Alright.
now. Thanks very much. Now we're gonna start the judgment questions. Yeah, for the judges, please raise your hand if you have a question.
So I have a question, but before the question, I think it's important for all of us to acknowledge that this is the first team to ever present at the first Quantum Hackathon in Egypt. So I think they deserve another round of applause for the confidence. Great job. My question is about the fact that you use both approaches, the universal quantum computer with IBM's backends and the annealer. What would you say has been the difference in the experience of using both of those methods?
Do you mean the D-Wave annealer and
Yeah.
the QAOA?
Yeah.
Actually, for the D-Wave annealer, we just run the simulator. We couldn't activate the real hardware of D-Wave due to some constraints. So actually, the main for the D-Wave experience, we go through some specific algorithms that shows us some tricks to minimize the complexity of the optimization algorithms, such as like slack bits, and also we would use something like dummy node, so it reduced the constraints, especially constraint of 3 patients per trip. 3 patients per trip. So we use this dummy node for making like the distance between this dummy node and the hospital is 0. It will not be counted. Then
part we're using the hyper solution, we're using the classical and the quantum at the same time. The quantum we assume that it's going to be as fast at some point. It's going to be faster than classical, and then we're using the classical model to actually compute the route. So we think the annealer it's much better. Basically, it's like a hybrid, but well, we were trying to prove that on actual hardware. If we could do that, we would definitely find a difference between those.
Thank you.
Thank you so much for your presentation. So I have a question actually concerning the hardware. So it wasn't like the Leap hyper sampler. So we just used the simulator from D-Wave. That was it. And then the second is actually a remark, just like a note for the presentation. So you had suggested the cubo, right? So that would be really nice if you had the mathematical formulation of the cubo, like in the slide, like the full cubo, like with constraint and objective to be able to visualize it more. Otherwise, thank you so much.
Practical question. So why couldn't you use the Bibliotheca?
We're actually we're trying to use the Qbert, but we didn't really have the access to run that. Basically, we're just waiting for the access. We submitted yeah, so that's all.
DWeb also like shows a great algorithms in that part, but actually they didn't like give us the full access for the real hardware. But when we see their efforts in especially the vehicle routing problem, they show good results for that part.
Okay, thanks very much. Okay, time is up. Okay, big applause. Big clap for our team here. And for the next team, please step forward. Team 2. And the jury members can use this time to fill in the form. Be aware that the jury members who are not gonna fill one team and they will miss one team, we are gonna remove their judgment criteria from the form in order to be fair with everyone. Okay. Okay, team 2 is ready?
Yeah.
Okay, team 2 is ready. Okay, please go ahead. So good luck.
Thank you. So, ladies and gentlemen, first of all, we're team carbon capture. And first of all, I would like to prove a point, which is chemistry is all around us, right? So, first of all, I would like to do the simple old school trick. Yeah. Coke and mint. It's pretty obvious. This trick, like we all see on YouTube Reels, and for us, like computer science, it's really a fascinating trick, which actually attracted us to deep more into that quantum chemistry problem, which is carbon capture. And now moving to neural.
Okay. CO2, carbon dioxide, is the main driver in our current climate change crisis. And to put the problem, to put the size of the problem more into perspective, in 2023 alone, the global emission of CO2 had hit 40.9 billion tons. And the energy sector is the main contributor, responsible for 73% of all the greenhouse gases emission globally. And with this overwhelming size of problem, our solutions are not scaling fast enough, as the current carbon capture capacity offsets only 0.1% of global emissions. And to solve this problem, one of the suggested solution is carbon capture methods. And the key to better carbon capture is to simulate the core chemical reactions. But simulation of the core chemical reaction requires a high accuracy, and this higher accuracy requires solving really difficult chemical equations that gets more and more complex for larger molecules. Um, Okay, our setup starts mathematically with the molecular Hamiltonian, and we took two approaches to solve this molecular Hamiltonian, the classical side and the quantum side. In the classical side, we used the density functional theory, which we used to solve the 0-point energy, and the DMT combined with the FCI to calculate the accurate electron correlations. In the quantum side, we mapped the Hamiltonian into qubits, and we applied the VQE with the UCC, SD, and ZATS to calculate the ground state energy.
As Noran said, we used to calculate the potential energy by using DMT with FCI. We couldn't use FCI alone because the molecule was too large. After that, we calculated vibrational energy by getting the frequencies from the wave numbers, which calculated through the DFT, and using the 0-point energy formula, we found the vibrational energy. Using all of this information, we tried to make a simulation by calculating the potential surface energy when we try to make the N atom attack the carbon atom. This is our results using a classical method, which shows that first the transition state, final state 1, transition state 2, and final state 2.
Thank you. Now I'm going to talk a little bit about how quantum delves in. This is a variation quantum circuit. Variation quantum circuit has some parameters, and these parameters enter into an optimization process. This process is used to get the best parameters in order to minimize a certain cost function. In this case, in the case of variation quantum eigensolver, it is used to find a certain ground state Hamiltonian using the adiabatic theorem, which is from a ground state to our desired ground state. And we try to calculate the vibrational and electronic ground energies. These are important in trying to understand the reactions that we have. Electronic energies are associated more with the electrons moving between orbitals and so on. Yeah, they are also about embedded in the orbitals, and the vibration energy is about the atoms itself, how they vibrate, how they break, how they bond, and so on. For example, this is a result for calculation of vibrational energy. As you can see, this is the graph while doing the VQE for our product, and the previous slide was for the reactants. And these are the comparisons between our VQE simulators on classical computers, the one on the right, and the classical methods that my colleague explained for CO2, NH3, and COOH. And you can see that the results are really similar at that scale. Of course, as the number of molecules increase, there are you model a lot of more energies, then you find a little bit of more difficulties. Yeah,
and for our quantum solution, out of curiosity, we kind of developed a way to calculate the reaction pathways by trying to delve into the radius of the bond length between the nitrogen and carbon, and then calculate the energy at each point. So it turned out to be like this shape.
We had amazing talks yesterday and the day before about some other new algorithms, which we couldn't leave the chance to test them. We tried to test the sample-based quantum diagonalization, which we used by ourselves on the NH3 because it wasn't available in the repository, unlike the CO2. We calculated it by ourselves, learned how the algorithm works, and decided to even move to calculate the product, the NH2COH, which is really large. But we made some calculations. We are still leaving it to move forward to get the results.
Yeah. So we study the atomic, subatomic molecules and particles. Quantum is all about that because quantum is these subatomic particles. And then As you can see, there were a little bit more difficult differences between the classical quantum diagonalization of the matrices, where the classical and the quantum was PQE, as I explained. Now, there are possible quantum advantages.
Possible quantum advantage is capability works for large dual systems where classical fails, direct simulation, not the quantum systems without heavy approximations, future impact. Carbon capture, we have vision that when I was read research, I found that we can make ammonium carbonate to a urea by capture CO2 from industrial emissions, convert it into stable immediate ammonium urea.
Okay, sorry, time is up. We have given you 10 extra seconds for the clicker problems. Okay. Big clap for our nice team here, and then we are gonna the judgment criteria. Please, we need questions from the judges we didn't ask yet. Good.
Chemistry basis have used 6301 basis, if I remember the code correctly. And for the product NH2COOH, we had 82 qubits. So yes, for CO2, we had about 57. We tried to make some frozen orbitals.
Actually, I'm impressed. Thank you very much for the nice presentation, short and nice. The only comment which I have that you need to talk about the use case in order to make it simple for people who are not doing material science. So out of the sudden, we saw CO2, NH3, and people start to ask what is the connection, what you are trying to do. So only the purpose. Other than that, what you have done, given the time that you've been given, is really, really impressive. Thank you so much.
Absolutely. Thank you so much.
I have two questions. The first one, did you try this on IBM, the real IBM quantum computer? Okay. What is the time comparison between the classical approach and the quantum? You didn't have time to show the quantum advantage, so I am giving you the chance to show this.
It was in the slide of the potential advantages of the scalability, as I said. Our quantum run, I think, is still on the cloud. But yeah, that's.
So I'm still waiting for the answer.
Between the classical solution and the quantum solution. The solution provided by the classical computing part is a little bit incorrect, or let's say inaccurate, because it had some higher values for transition state 1, which shouldn't have been, because transition state 2 should have been higher. So for chemistry problems, we talk a little, or with our understanding, of course, we think of feasibility and the correct modeling rather than times here.
Just because I have the time for the answer as well, the main purpose was, of course, carbon capture, and the utility was to make urea, which is used for agriculture. While I have the 5 seconds.
Thank you.
Thank you very much for this interesting presentation. So, I mean, I have concern here about training. You said you're using 83 or 84 quantum qubit, right? How many layers in the answers did you use? Yeah. No, you said you used VQE, right?
Yeah.
So Variation Quantum Eigenvalue Solver is based on answers, as you said. And
Yeah,
you
yeah.
have the number of layers.
Yeah.
So how many layers did you use?
well, in this quite run, I don't remember exactly the number. I can check it out after that. However, the big number of qubits is mainly because of the embedding, because we choose to.
No. I'm saying about how many, because this actually translates to the number of parameters. So how many parameters do you have with the variational quantum circuit? How many parameters do you have?
I don't have it here, but
yeah, because at least you'll have 83 parameters, right? And training 83 parameters to compute the gradient, you need to use the shift rule, right? So I would assume the training time will be tremendously large. So I have a concern here. How did you manage to train quickly?
It didn't actually finish training. Because we just like left the job and then we came here because we tried to simulate, but they haven't really received.
Okay, so yeah. So now we are gonna just for the fairness with the other teams, we are gonna stop the question.
Thank you.
Thanks for the team and thanks for all jury members for the nice questions they have asked. Big clap for our team again. Yeah, because they choose chemistry indeed. It's very our favorable topic. Okay, the next team, please step forward and please for the jury member to use this time to fill in the form of the judgment. Be aware that the jury member who is gonna miss one team, his criteria or her criteria will be omitted for the fairness of the rest of the teams. Okay. Team 3. Where are the members of Team 3? We have 4 members only. The 5th is missing. She's here. Ask her to put her back away. Okay, so okay, please start.
Hello, everyone. Every second, 1,000 metric tons of carbon dioxide are released in our atmosphere. This statistics is from the International Energy Agency. This amount of carbon dioxide threatens our lives and the lives of our future generations, and a lot of effort have been put to limit this. However, carbon capture is an innovative solution from a different perspective to solve this problem. Okay, with carbon capture, we can limit or reabsorb the carbon dioxide emission and have better byproducts from this chemical reaction that can be used for positive applications. Quantum chemistry, however, quantum chemistry provides a better models to simulate the carbon capture process than the classical model. It enables us to have a better simulation. So if we in the future going to use better molecules than, for example, ammonia, which is our problem, we're going to need more advanced models to exactly predict the reaction, and it will help us develop or find or research materials that can help us in this. Okay. However, in our problem, there is the basic. In order to model this problem, we need like 46 qubits for the carbon dioxide and the ammonia molecules. We would like to need to minimize them using an active space and having an STO3G base. So now my colleague is going to continue the next slide.
Okay, let me give you a tour around to know what we did in the computational classical model we did. So actually we did just 4 steps. My first step I have is a setup. So I have visualized all the atoms we have like molecules, carbon dioxide and ammonia. So We have three phases actually to combine it. And after that, I have used DFT. First, we just get all the electronic energies, and we have applied it on the diagram here. I will show you. After that, I have used BES scan. We have used it to get the binding energy, because if the binding energy getting down, that means the molecules can interact easily. So I have made all the diagram here and get the slowest point here, and it getting me what is the minimum binding energy to make this interaction. And the distance we have is 3.2. It's the perfect distance to make the two molecules interact together. And after that, I have did vibrational analysis. So I have did the vibration and frequencies have actually a lot of important. It's too important to understand how interacting between the molecules. So this vibrations between CO2 and NH3 separately, just to study this case and know actually this interaction, how can be done. So after that, I have made measured by HK and CSSD, and I make just VS. It's a reaction pathway of the combination in H2COOH. So we will find here the process I have did to get the hexagon matrix I have used in this court. This is all about the classical computation. Let's go.
Okay, now is the quantum model. Why we use the quantum? Quantum is basically the language of chemistry. So it's perfect to get better results for the electronic configuration. Our methodology, we started first by using VQE, but we then transferred to SQD because we found that our problem is a bit complex and VQE couldn't like perfectly get the results. And SQD was like better to surpass these limitations of VQE and to provide reliable results for the reaction pathway. So what are exactly the advantages of SQD? It gives accurate energies, as I said, and it's fast and efficient. VQE used to have like a very long runtime to give us results. And it's when applied to like hardware, it's more of noise friendly. And it directly maps to the reaction pathway. We don't need like to have a midway like we did in quantum to transfer to the reaction pathway. And this is for the code workflow, how we implemented it. We started by building the molecules. We defined the NH3 and CO2. And then we did something called Hartree-Fock to get like an indicated guess for what will we get for the energies. And then for optimization, we did active space selection to get only the valence electrons to participate in this interaction, to not have like a very large number of qubits. And thus, then for the SQD step, the major step of the SQD algorithm, it has like two parts, quantum part and the classical part. The quantum part do something like called bit strings, which is like sampling the electronic configuration in a cat sampling. The classical part is clustering all these bit strings to find which one is the nearest one to the one we got using Hartree-Fock. And then we simply model as in the graph, we get the reaction pathway. Then we compared both the classical and the quantum, and we found that these are the graphs. The first one is classical and the second is quantum. We have for sure some limitations for our projects, like time limitation. Hackathon is very short term, so this is mainly it. So if we got more time, we can further optimize for this algorithm. And the data limitations,
quantum is still under development, so we don't have like large data. And technical limitation due to the software we are using is not developed enough to run like more advanced algorithm. And for future recommendations, we need to do error mitigation for real quantum hardware, but this is more complicated, very complicated actually. And we can use like a hybrid system using quantum and classical and optimized. Thank you.
Okay, thanks very much. Team finishes on time indeed. Okay, time for question.
I just wanted to give you a chance to elaborate on something that I think you missed. The graph showing the difference or the comparison between the classical and the quantum. You just skipped over. You just showed us the slide, and then you started talking about the next slide. Could you at least elaborate for half a minute about it?
Okay. Okay. Actually, this graph is the same of this graph, but it's just simulated. It's have a lot of simulation. So let's focus on this graph, okay? It's have the same pathway, but it's just a line here, give us all the variables, okay? So what we have got of this graph, actually, here we have our key simulation. This is noiseless, the blue, and quantum devices red. It's what version we have used, SQD. So what we got of this graph, so the energy, this line is when this two have totally be the same wave, has the same wave, and it will be continuing to infinity, okay? So here it will be separated, and after that, it will be just merged. Then we will get the energy of it, and it will be the CI energy. So from this graph too, we have noticed that the classical graph actually is down of the quantum graph. And from calculation, when we logged out for another document and paper, we found that this graph is more accurate than the classical graph actually, okay? So we have a lot of information of this graph actually, because it's too complicated. And this is done actually. Thank you.
Thank you very much for the work that you have done. I think there is a typo in one of those slides where you mention HK. It should be Hartree-Fock, HF. And my second question is, surprisingly, you get the result using Hartree-Fock, which is an approximation with the most accurate classical approach, which is CCSD. So can you elaborate about it? And my last question is, how many qubits did you use? Just out of curious.
Okay. Sorry. Number of qubits. Yeah, we have used the. I can show you the graph. So, okay, no, okay. We have used 8 qubits for this simulation, actually.
And why Hartree-Fock is more accurate than CCSD, which should be more accurate method. This was a comment of our colleague here. Yeah, please go. Why Hartree-Fock gives a more accurate result than CCSD method, which should be more accurate than Hartree-Fock.
Okay. Get back to the classic. It's mine. Okay. Here, the CSSD is more accurate because it's relying on
Actually, CCSD, it's when it's have two single excitation and double excitation. The single excitation here, it's just pushing out, like a pushing out one electron from the ground to the excitation. And the double excitation, we have pushing out to our, make the electron jump to the, two electrons jump to the excitation state. So in CSSD, we have reading a paper said that if I collect the T1 plus T2, it will make me have more accurate, okay? So the graph here is not just CSS DT1 or T2, no, it's the collection of them. So it make it more accurate than anything. And actually this the comment specifically was so fresh actually. And when I read it, it's some kind of 2022 because it's a fresh paper. Okay, just that. But the HK is just relying on one of them. So the CSSD.
Okay, so time is up.
definitely-
So yeah, we give you more 10
definitely.
seconds, and hopefully the answer is clear. Okay, big applause for our team here. And yeah, thank you very much. So it's nice work. Okay, so give a few seconds for our jury members to write their judgment. And for the next team, please step forward. Okay, where is the next team?
Good afternoon.
Okay, please set the counter to 8 minutes. Okay, team 4 for all the jury members. Please don't forget to write the team number in your form. Okay, the counter is ready. Okay, please get started.
Good afternoon. Today, we represent routing optimization for crowded city, taking new capital as a test case for us. Cubo is our team name. This is our team. Amr Ayub, Basil Ahmed, Hamad Ahmed, Hassan Khalifa, Yusuf Kamel. Mentors, we have James Austin and Dr. Ahmed Said. And here, why does this matter in doing routing optimization? Think of emergency situation where every second matter. Here we have some looking at statistics. We can see how a couple of seconds may differ in emergency arrival or CPR treatments. And this is just two statistics. There are a lot, hundreds of statistics about this. Okay, table of content, we go through our classical approach and quantum approach and comparison between them and future direction. Our constraint, our challenge we are trying to solve, we have one hospital, 5 patients, and we should get the optimal route that we have constraint of 1 ambulance and 3 patients per trips, and we must get the optimal. Okay, thanks. Basil, continue.
Okay, so for the classical approaches we explore the diverse set of algorithms to help us better understand the problem and its limitations. So we went through brute force, heuristic, A-star search, mixed integer linear programming. For starters, the brute force, as you all know, it explores all possible subsets of the graph, but it with a large number of ends and nodes. It explodes combinatorically. Next, the heuristic approach, we chose a greedy heuristic, meaning that we choose the closest node from the node we are currently in. It yields minimal execution time, but it doesn't guarantee an optimal solution, not always. The third approach was the A-star search. So because our problem simplifies to a graph problem, we thought, why not use a graph search algorithm? But why A-star exactly? Because it guarantees to find a solution if there exists one, and we know for sure that there is a solution because it's complete and optimal. The last was the mixed integer linear programming, and using our objective function, which is the distance metric, and our constraints, which is visiting each node only once, we can formulate the problem using these linear constraints and objectives using any mill backend or solver. One was OR tools that we used, was from Google, and the other was Cplex from IBM. Next, these are the results that we reached for reference. And next, we are going to discuss the quantum approach we took with.
For the quantum approach, we first started by looking for a paper with a similar problem, but we found one, but it was a bit too complex and too big for the specific case we're using. So, and it uses about 180 qubits. It would take about 180 conditional variables, which corresponds to 180 qubits. So to minimize this, what we did, we assumed that the optimal solution should take 2 trips because because on average, any more trips would require you to go to the hospital to another patient and come back an extra time. This reduces it to 60 qubits. Then we could reduce it further by using putting the 2 trips inside the constraints of our objective function. So our objective function becomes like this. Instead of 3 summations, just 2 summations, and it will take about 30 qubits. Our first constraint is any node you enter, you leave. The second constraint is you leave the hospital twice, which is 2 trips. The third constraint is you don't take 1 patient at a time. You take more than 1 patient every trip you take. And the fourth constraint is you have to visit a patient at least once. Next, Muhammad will present the
in the qubit formulation. We have first converted our constraints into penalties using the table we got from the paper. Then after this, we have combined it with the objective function to get the qubit equation. This qubit equation we have used in the QAOA by using the qubit function, mapping it with Isaac Hamiltonian. It converts to cost Hamiltonian. Cost Hamiltonian is using in QAOA, alternating between cost Hamiltonian and mixer Hamiltonian, while a classical optimizer to the parameters. And another quantum approach, we have get it in 25 qubits instead of 30. And we have used another approach, and this is the map, and we had got near it by 60 kilometers instead of 57 kilometers. And there is another approach that we have used only 5 qubits that have get us to 68 kilometers instead of 57. It was more inaccurate, but it gives a better efficiency optimization. And next with Hassan.
Okay, what is quantum advantage? Okay, like if I do this problem
similar to in the classical, I need factorial of the number of the patients. So the nature of physics and least action move with using this Kubo form and put it in Hamiltonian, we can the quantum see all the solution and give the minimize the energy, which is our cost function. So also, okay, about hybrid approach, which we can calculate the classical and quantum. Like, what if we do divide the number of patients and get the numbers, three of them, and try using traveling salesman person on these three, like because three trips in the ambulance is not a scale like the number of patients. In the end, I want to say, don't give up on your dreams. And we can do it plus ultra. Thank you, guys.
Okay, thanks very much for the team here. Big applause to them. And now start judgment.
Okay, thank you very much for the presentation. So actually, I have a simple question. What's Quabble?
Binary. It's a way of encoding.
Okay, and you know what's quadratic opposition means?
Your problem, go back. The objective function is quadratic.
Yeah.
It
So
becomes
can you show me
quadratic.
the objective function?
Objective, oh, sorry. Yes. Okay. This is the objective function. This is a binary variable, so you can square it, and the value would still stay the same.
So that's why it's quadratic, because I can square it and stay the same. No.
This should be x squared. This has other quadratic
No,
forms.
it's because the d times x you have. You have two terms here. It's not the x squared.
D is the D for this for our
right.
function.
Anyway, how many layers do you have in your QAOA algorithm? How many layers do you have? 2 layers. Only 2 layers? How many qubits?
We had two versions, as I said. They are 25, and then we reduced the number of qubits down to 5 qubits just to get like a better optimization. And that's it.
Okay, and how did you convert this representation into quantum?
We just use the quadratic program provided by the Qiskit library.
Oh, okay, it automatically converts. Okay, thank you.
Thanks. Any questions?
Actually, I couldn't understand how could you reduce the number of qubits from 60 to 30 to 25 to 5? How has this been done, and what's the effect of changing this number of qubits?
The 60 part in the initial.
Just answer without showing it.
Okay, in the initial objective function, it's 3 summations, and it's number of trips times number of nodes you have and the number of nodes you can go to. That's 2 times 5 times 6, which is 60. So to reduce it, we can, instead of looping or like summing over every trip, we can just encode, like put a constraint that makes it take 2 trips instead of.
Why 2 trips?
We said 2 trips because anything more would be trying all of the possible trips would take a lot of qubits. So we said using 2 trips would be a bit.
So you reduce the number of qubits because you know the answer in advance. Right?
No. The two is because it's if we add another trip, you have an extra edge because you have to go leave the hospital and come back again, which is on average would be more than 2 trips. That's reason. That's why we made it 2 trips.
What about 25 and 5?
Okay.
I'm sorry that this wasn't really clear in the slides, but the way we did encode the qubits in the 25 qubit solutions and the 5 qubit solutions was different from the first attempt. So in the first attempt, the qubits really represented the edges between the nodes. But in the second attempt, they represented a subset or like a closed path that I can go in the search algorithm.
Okay, so you are looking to for minimizing the distance of the whole trip, while the most crucial parameter is the time, because for a patient and an ambulance, time is more important than distance.
Yeah,
I understand that it's a more difficult problem. Any comment on that? Maybe for future work, minimizing time instead of distance.
Okay, I might suggest that.
Yeah,
like
thanks. Time's up. Now we have given you a couple seconds. Big applause for our team here. And for the next team, please be ready and step forward. And while the jury members use this time to fill in the grades. The current team was team 4. Okay, the team is ready.
So,
5 seconds just for our jury members to finish the grading.
Hi everyone, this is Bimela.
Sorry, we just we need the counter to start here. Okay.
like a lot of which have like a lot of predictions. So this is why we choose like this problem, which problem. Go with
Okay, so we're gonna speak about pre-processing and maths. Mainly, we found the paper speaking about the same issue. Okay. Okay, so can you hear me now? Okay. So we found the paper and it was speaking about the same issues, salesman's trip. And we decided like we didn't find any implementation and we tried to find the implementation for it. And using the coordinates that we got. So we use snapping with the open browse services or ORS to align the points in to the rows and to the graphs that's going to be produced by the code. In the cost matrix pairwise in distance in kilometers, and our formulation was these objectives, and our constraint were the 5 patients visit were picked by in 2 trips by the ambulances to the hospital, and we tried to make each cluster together to be picked up in one time. And also we had a patient in the middle of the desert. So we decided like, yeah, we're gonna try to find the best route to it and in the nearest point, but every other patient was in the exact place and we had got it. Now we're gonna speak Muhammad.
Okay, we are going to talk about the classical approach. We like use the brute force and the greedy heuristic. We start with the brute force, like we literally do all the probabilities that the nearest or the minimize the this distance. So we find that that the best brute force we use for the approach is 3 patients for the first trip and 2 patients for the second trip. And then we used like to compare with our brute force, we used the greedy heuristics. So we find the nearest parameter or the nearest variable to take it, and we just like the two results is exactly like the same. That we find that the two results is 57.33, and the heuristic must like got approximate, but it gives the exact number because the number of parameters is small, so it gives us the exact number of the brute force, and the brute force that must give us the optimal results. And like we
Okay. Hello, everyone. So now we know how we did it classically, and our whole hackathon is about how we do it in the quantum world. So now we have our C matrix, which is our cost matrix, and we use that to formulate it into our quantum solution. So we had the cost matrix, and then we have verified it with sanity checks, of course, using the heuristics and the brute force methods. And then, okay, so now we have assumed that we are going to go over 2 trips, 1 trip that is 3 patients and 1 trip that is 2 patients. Okay, so for our classical, we were created deterministic. So how we're going to do it in the quantum realm? So we're taking our vehicle routing problem and we're trying to make it into cubo formulation. So we introduced the variables z sub r, z sub I, and z sub p. So r is for routing index, which is either 1 or 2, like so the group that has 3 and the group that has 2. And then we have the patient index, which patient it is. And then we have p, which is position in the route. So basically their seat in the ends. Okay. And then for us to turn it into cubo, we need to have some constraints. So our constraint was each patient appears exactly once, and route 1 has exactly 3 patients, and route 2 has exactly 2. And we also assume that if we started with the second route and then we went to the first route, it's gonna be the same. So 3, 2, or 2, 3, doesn't matter. And then we can't have 2 patients in the same seat, of course. Okay. So we made our quadratic binary, and then for the okay, so for our coefficients, we made a matrix. We called it Q dense, and then we took that matrix, and we made our Hamiltonians. And using our Hamiltonians, we ran it over the quantum hardware, IBM quantum hardware. And we ran 16 circuits, and we tried to find which Hamiltonian had the best energy, and we took that. And then basically each Hamiltonian had 2 variables, gamma and beta. And we took the gamma and beta from the best Hamiltonian. We ran it over another circuit. Okay. And then that circuit basically gave us our bit string, and we took that bit string and we decoded it, and we got our our best routes. So our best route was 57.7 kilometers, which is only a little time in a bit worse than the brute force, which is our reality. And the reason behind that, because basically it's a very small problem. So that's why we got such a solution. And sometimes our solution was up to 70, and that was only because whenever we ran the circuit again, and that was only because of quantum noise, and that's it.
Thank you very much for our team here. Big applause again, and we're gonna have questions.
Thank you so much for this great presentation. So I have a quick question concerning the penalty term. So what was like the penalty term that you have chosen for the constraints?
Penalty terms were based on 3 constraints. So the first constraint was that we can have one patient per the patient can be in other trips, like one patient in the trip. The second one, we can't have this we can't have 2 patients in the same seats, and also
So you just translated the constraints into
yes,
penalty
yes,
term,
to the
right?
penalty.
Okay, okay, thank you.
This will be a little bit of comment followed by question, right?
Of course.
So one of the things, this is what I do for a living, by the way. So
yeah,
if it's too hard, just stop me. Okay. So one of the things you've done, actually, you set a heuristic when you say you have a 3 plus 2. All right. This has tremendously reduced your
exactly
to
because
5 choose 2. Right?
Yes.
So you're looking at a quadratic. Okay. And my friend over here, he said that we reduced the number of it solves exactly because the number of constraints is small. Do you have some sense of where this breaks down and when quantum really takes over? Because at such a small scale, you can run it brute force in a fraction of a second and get exactly right.
Exactly.
Do you have some sense of where the quantum takes over and solving better or quicker?
Like for now, we give an example, or we do a research that if we increase the number of patients from 100 to 1000, the quantum will solve it from few in a few hours. But if the quantum right now, if we really increase the number of patients to 100,000, that will take a million of years. So right now, the quantum do things it's, I can't say it, but it's medium, yeah. But yeah, it's so number of patients 1,000 patient is good, but it's not the greatest thing until now. But in the future, we said it can solve 100,000 patients in a few hours. We don't know.
Add to that we're only focusing on the time complexity, not the space or the energy complexity. And any other questions?
Thank you. I just have a very simple question. You said your objective function is minimizing the summation of Cij multiplied by Xij, right? Can you explain?
This is the cost matrix.
So what's your objective function?
Objective function, we used QO, and I really want to understand the
But
question.
objective function is more about minimization or maximization, right?
Okay.
And I think this is the
So,
objective function.
I can say it in a very abstract way, which basically
No, just simple math, right? I just want the math, right? What's your objective function? I think you wrote it as minimization of summation of Cij multiplied by
yeah,
Xij.
exactly. Yeah,
I
yeah,
think
yeah.
this
So
is
we're trying to our objective function. We're trying to find the least distance between the nodes.
Yeah. So my question is, how can this formula of summation translate to what you want to achieve?
Oh, thanks, Dr. Ahmed.
So much.
Okay, thanks. Big applause for our team here. And please, for the next team, please step forward and be ready while our jury members take their notes and put the grades on. We had the team 5 now, and the upcoming will be 6, but 5 for the grading. Okay. Okay. All grades are on. Okay.
Q medicine, where quantum AI makes health. This is our team. Imagine waking up someday and you lose control of all your body and you don't know why. This is exactly the problem we're gonna state today. Parkinson data disease is a disorder that the challenge really faces doctors. Why because of 30% of make 30% of the neurons making the early detection hard. This is what makes early detection matter. In 2019, around 30% of 300% of 300 person died because of this disease. That's what makes doctors suffer from this challenge, making quantum AI and the AI machine learning bring new hope and give a new solution.
For our dataset, we have 188 patients and 64 healthy persons. The age range is between 33 and 87 years. Our data size is 756 instance and 754 features. The binary classification here, or our task, the target here is binary, so it's either 0 or 1. So starting with the classical part, we develop neural network model. We start with processing part, and then develop our model, apply it on trained data, and then on test data. For the improvement, we apply voting classifier and feature engineering. The second classical, the classical for the first model is the accuracy with 95.2900%, and the graph here show us the accuracy and the loss over the epochs. Our second model is SVM. We processing our data, and then we train our model in RPF kernel, and then evaluate our model in testing data. So here the graph show us the train accuracy and the test accuracy. The most exciting part is Rana.
Why we use quantum machine learning in the first place? High dimensional power, speed advantage, and deeper insights. But full benefits depend on future fault tolerant and quantum computers.
Okay, for our quantum solution, we decided to use VQC as the simplest and the general solution for all quantum machine learning problems. So first, we need to know how can we convert the classical data into quantum data. So we used quantum encoding. We have 3 approaches to encode the classical data into quantum data. The first approach is to use angle encoding. Angle encoding is to convert the classical data into some rotational angles, and each qubit is mapped to one feature. But for this type of encoding, we have to do some PCA because our data are over 700 features. So we used PCA to reduce the dimensionality, and also we selected the most correlated
features. But honestly, we used feature maps, and especially we used Z and ZZ feature map. Why feature map rather than angle encoding and amplitude encoding? Because angle encoding is amplitude encoding first is very noisy because of its circuit depths. So we decided to shift to feature map because it's more sophisticated than using angle encoding. So we used that and ZZ. Then we used some answers. It's hardware answers. This is the full answers. So we used real amplitudes and efficient SU2. We do some repetitions for the answers to get higher or the suitable thetas. It's about to get to reduce the loss and select the most suitable theta for training. So ansatz is about it's about some circuits to get the thetas. But how about the optimizer? Optimizer is just to we use the optimizer to select or I don't know. The optimizer is to use the reduce the loss of the theta to choose the suitable theta for our vector state or quantum state. So as we see, the accuracy for the for the 4 qubit and Z and real amplitude and 10 repetition and SPSA is 75, but it's not promising. So we decided to convert into SVM, QSVM, and this is the board of my teammates.
So beside the BQC model, we implemented a quantum SVM model. So of course, we started with pre-processing, used scaling, dimensional reduction, handling imbalance classes. The methodology of quantum SVM, we started with encoding the features into. We started by encoding the features into quantum states, and then used quantum kernel to measure the similarity between the states, the samples. Sorry. Then I used more than one amplitude, more than one encoding technique. As we can see, angle and amplitude. The amplitude is performed better with accuracy 82%. Quantum versus classical, as you can see, best quantum SVM model accuracy is much closer to the classical one. Time's up.
Okay, thanks very much. Time is up.
I have to get to some.
No, time is up. Okay, time is up. Thanks very much. Okay, now we start the jury member.
Yeah, thank you very much for your work, and I actually like what you did. Actually, yeah. So thanks for that. And I just have simple questions about like what problems did face you when you run on the? Did you run on actual quantum processor, right? Right. So what problems did you face? I mean, the quantum training or when? So what challenges did you face?
Massive number of features. Them. Each time we try to take much time to make them.
Okay, did you try to change like how to say the number of shots? How many shots do you use?
For the quantum SVM, it's one-time run.
Used run
Number of shots
for the hardware.
Yeah, for your variation.
For you mean for the simulator? We used 1,000 shots. for the simulator.
10,000.
No, 1,000.
1,000.
1,000. Yeah.
Oh,
But
okay.
the problem is our data set are about over 700 features. So to map the classical data into
I
quantum
take it.
states, we have to reduce the
I
the
agree.
feature.
But my last question is, you only use 6 qubits, right?
Yes.
So why didn't you increase?
It's about for our case, but as a future work, we have to increase the number of qubits and also to
Because you
use
had very
quantum
good
inspired.
performance here, yeah. Anyway.
Okay.
Oh, quickly. Okay. Another comment. So I also work on this. The interesting thing is that you've chosen accuracy as your measurement here. And that's not really what we want, right? This is Parkinson's disease. We're willing to give up a few false positives, but false negatives is really, really what you want to minimize. So if you were going to rerun this again, what would you do to give that measure?
Actually, as I said, I need to change the answers because I use hardware answers. So I need to convert into quantum inspired answers for the solution itself to be specified for the solution. And also I need to increase the number of qubits because the number of qubits means many features can represented by the qubits and many features make the accuracy becomes more and more.
Thank you very much for what you have showed and walked us through. Actually, I want to take the discussion for another level. So one of my question is, do you have any sort of elaboration why there's a difference between the accuracy, for example, between quantum? This is my first question. The second question is, how deep was the circuit, the quantum circuit? How many gates? And have you tried the transpiler function in IBM
Honestly, no.
to
Honestly.
optimize it, reduce the depth, which may increase the accuracy?
Honestly, no. But for our problem, using quantum solution was not promising actually because the highest number of features, as you see, the SVM is accuracy to 92, but going to the quantum SVM is just to 28, 82. That's because as I said before, the features are over 700 features.
Yeah.
So
But also there is another element. For example, the encoding approach may have another effect.
no. The feature maps is the suitable one for our problem.
Thanks very much. This is Team 6. Okay, big applause for Team 6. Then, yeah, for the next team, please be prepared and step forward. And while our jury members take the grades. Okay. For our jury members, please take the grades.
Yes, please.
Team 7 is coming. Okay, the counter is ready. Please start.
Good afternoon. Our problem here is smart traffic optimization in the Neo Capital.
This is our team. We're team 7. This is the traffic here in Egypt. So Egypt is shaping its future with new cities like Sheikh Zayed and new capital, designed to represent modern living, sustainability, and smart infrastructure. With traffic here, it's not only waste of fuel and time, it can also risk lives in emergencies. Picture this: an ambulance want to pick multiple patients to a hospital. Every route choice matters, and a few minutes of delay can change everything. To our real world problems, hospitals and emergency care, police and security, firefighting and civil defense, metro and public transportation, school and public services, and smart city logistics. This is our table of content.
Okay, I will speak about the problem definition. It is the same problem definition over and over, so I will be short as soon as possible. So, okay, our problem is a variation of the traveling salesman problem, the classical one, but it has a different point. But however, we have some nodes, and the traveling salesman problem should pass through all the nodes with the shortest path ever. Okay, that's our scenario. We have an hospital here, and the ambulance should pass through all these patients. That's our problem, our scenario. The difference from the classical public salesman problem is that we have a limited capacity for the ambulance, which is free. So we have to go through the 5 patients on multiple trips. Okay.
Okay, for formulation and pre-processing, we make a comparison between the Haberson and the OSRM to just know which method is available for our problem. Quickly, Haberson is a mathematical formula to calculate the shortest distance between 2 points on sphere using their latitude and longitude, but it ignores route networks, traffic, and trade. While OSRM it can optimize routes for multiple patient and location, and it's high performance routing engine built on OpenStreetMap data used to compute real world road distance and routes. This is our distance calculations as you see. Okay, so we are going to get the shortest path to get all 5 patients through both classical approach and quantum approach. Worst case approach is to take each patient from his place. Like here, for the first patient, this is the route from hospital to a patient GR, from hospital to patient R2, as you can all see, from hospital to patient R3, and finally from hospital to patient I3. With total distance 110.55 kilometers. Remember the function.
After knowing the upper bound, that is 110.55 kilometers, our classical optimization, we use two strategic implementation, which is brute force and greedy. For brute force, we try all the possible routes from the hospital to every patient and try to find the optimal solution. We provide this algorithm provides us a guarantee of the shortest possible distance and only works. But the problem here, it only works with a small number of patients. As number of patients increase, it grows exponentially. And the lower bound here is 57.31 kilometers. For the greedy approach, this is the upper bound used by the worst case and the lower bound used by the brute force. For the greedy approach, it begins from the hospital and chooses the next shortest path, and then repeats until it finds the maximum stop that is 3 faster in execution, but it doesn't guarantee a global optimum, and it performs decrease. Okay, for the classical challenges, we have we have a scalability issue, computation time, greedy trade-off, and dynamic traffic conditions.
Now for our quantum approach, first we need to define our mathematical space. We define an ordered pair, P for a set of patients, E for a function as a map that must satisfy those two properties from P to the same P. D must equal 0, otherwise must be bigger than. Okay, firstly we defined it as a Harbison formula. Then we use the OSM to get more realistic path distance. We defined our cube variables at that X and J and T. If patient I is visited at stop J of trip T equal 1, okay, it's true, else will be 0. For this, if we compute, it will be 30 binary variables, which already will be 30 cubits. Our constraints mainly is that, okay, every patient must be visited exactly once. For all I, will enforce the third constraint, and the 3 will enforce the second constraint. Okay, this is our objective function. We try to minimize the total distance. Those terms, what makes it quadratic? Okay, H in the first, to enforce, we start from hospital, H in the and to enforce that we must end in the hospital, start hospital, steps, hospital. Okay, our implementation formula to map the QO model and solved with QAOA using Cascade. However, in practical, running QAOA with 13 qubits leads to exponential growth in time. To mitigate this, we try to eliminate one dimension. So we try to eliminate I. Actually, we eliminate J, okay. Dropping the J dimension in the quantum layer, thus qubits from 30 to 10. Then we applied a functional F from classical filter that validate the third dimensional. Okay, then it print only the validate solution, otherwise will not print. Okay, we run this simulation 122 times. Minimum value was the
time is up. Yeah, thanks very much. Thanks very much for Team 7. Yeah. Questions?
Thank you very much for your presentation. Can you please elaborate on this?
Okay. Okay. This the count of time I run the simulators. Meaningful total distance was 63. Standard deviation is 4. Okay, minimum value was the classical value that we got when tried the brute force. Okay. Okay, max value was 68, which is good. This is the distribution total trip distance. Okay. It's very close to the classical one. And this is a trip 1 with trip 2 distance. And if we saw it, let's try to go to the barrier of the quantum, barrier of the classic.
Okay, just to keep it fair for the other teams. I had a follow-up question about the trade-off that you faced when you reduced, or you moved rather, the J dimension. So you said you reduced the number of qubits, I think from 30 to 10. What was the trade-off in your accuracy for the calculations as a result of that move?
Okay, when we dropped the J, which is the stops, and added it as a filter, this add complexity ON plus LJ. Okay, so it is try to J every time it attempt to find the valid solution. But it is good as when we try 10, maximum 9 attempts, we got valid solution in 5 minutes. 30 was run for 2 hours and didn't get any answer. Thank you.
question. So in order to evaluate the effect of reducing 30 to 10, you need to have a benchmark. So have you tried to benchmark this with classical to see the effect of the reduction?
Okay. 30 qubits was running for 2 hours and didn't get an answer. So we couldn't check the optimum solution for 30. We tried to run on IBM, but first we need to convert to Ising, then applying on IBM as for modern casket, it doesn't do that automatically.
Yeah,
But
but
we
just to
didn't have
make
the
it
time.
clear, you run it on a simulator. It's not the hardware because
Yes.
yeah.
It's still Cubo. We didn't convert it to Ising yet.
Okay, and have you benchmarked the results with classical to see the difference between?
It is in the compare. I will let my colleague do.
Yeah. More questions or?
Just let's say in classical, it gives us one solution, but in the quantum give us a range of solutions. It's between the minimum, which is 57.31, scarcity is the mean, and the longest was 68.
Okay, any more questions?
Yeah, thank you for your effort. Again, I think the same question I asked before, Wabo, right? Do you have constraints?
Yes.
So, but this is, as you know, it's unconstrained by an opposition problem. So how did you account for the constraint?
Okay. This is the only constraint. The other tools can be
Yeah,
driven
yeah.
for the
So
bad.
how did you account for that? You said it's unconstrained binary optimization, right? So how did you account for this constraint?
Okay. Okay. In the objective function, there is two terms in the middle. Those are quadratic terms. Okay. Either true or false for the two terms. Only true if the patient one take from the S1 and patient two take from the S2. It is only true in this case, else it will be zero. So this constraint will be valid.
Thank you. Yeah. Big applause for Team 7. Yeah. So while our crew is preparing for the entrance of our online team participants, yeah, we give the time for the jury members to give the grades. Oh, okay. And now we finished with team 7, and next team will be team 9, not 8. Team 9, because team 8 will be at the end for technical reasons. Yeah. So team 9 is next. Team 9. Okay. Just okay, a kind reminder, team 9 is coming, not 8. Team next one. Okay, all of the members of team 9 is present or not?
I guess only me. Hello.
Okay, all the team members are present?
It's only me here.
Okay, can we see you? So can we make an eye contact with you or ممكن تفتح الكاميرا بس لو أمكن يعني.
1 minute if I
شوف مثلا لو
can.
زمايلك يفتحوا الكاميرا معاك ولا حاجة. في مش دول زمايله ولا؟ واحد تمام. طب معلش هتعرف اسمك بس انت وبتبدأ والتيم بتاعك وتقول اسمك بس بالكامل عشان نعرفه في الريكورد وتبدأ على طول مش هنقول لك يعني. ماشي زكريا؟
أيوه زكريا.
Okay, now we are with team 9. Are you ready?
Yes, I am.
Okay, floor is yours. Yeah, please start.
Okay, so good afternoon, everyone. Our presentation is about Parkinson disease classification. We are Team 9, Pupils, and our mentor. So, Parkinson disease is a progressive neurodegenerative disorder, and earlier the diagnosis can significantly improve patient outcomes. Our goal in this project is to classify patient with Parkinson disease versus healthy ones. We aim to evaluate how well classical machine learning methods perform compared to quantum machine learning approach, specifically in the quantum supervector machine. To ensure fairness and robustness in our model, we applied some main pre-processing steps. First, we start with balancing the data set using oversampling technique. Second, we perform over selection. And finally, we apply the principal component analysis to reduce dimensionality and avoid overfitting. So we move to the classical part. On the classical side, we trained 4 models, which is multi-layer perceptron and cat boost. Third one, it's random forest, and final one is XG boost. Here is the code workflow. Each of these models followed by the same pipeline as we mentioned before. So the results showed here clearly differences where the multi-layer perceptron and a random forest gave us moderated performance. Both achieve strong results, but as we will see after that, that the XG boost the best performed, which achieved the highest accuracy and stability across the experiment. So, if we talk about the quantum approach, on the quantum side, we implement a quantum supervector machine. We used the Pauli feature map with a fully entanglement to encode our data into quantum state and then compute to the quantum kernel. The quantum supervector machine was trained and tested using the same process mentioned before, allowing us to directly compare it with the classical models. So the quantum supervector machine produced a competitive results showing strong performance, especially when the feature space was reduced with the PCA, while didn't outperform the XG boost model in this experiment. We can see that clearly in this table. It demonstrates that quantum kernel methods are already capable of matching classical baseline. We can say that. So here in the table, we can see a direct comparison where among the classical models, XG Boost clearly stand out as the best performer, achieving the higher accuracy. Quantum supervector machine results were competitive to the cat boost and the random forest algorithm, showing that quantum approach can already achieve similar outcomes. So to conclude, we are looking forward to take the both models XG Boost and Quantum Supervector Machine to demonstrate high efficiency for the PD classification. And in the next step, we look forward to test some other feature encoding and other answers. Thank you for your presence.
Okay, thanks very much, Zakaria, for your nice presentation and your presence as well with us today. So now we are gonna have more questions for you because we have an extra time indeed. So
yeah.
hopefully don't fly away. So yeah. Any questions?
Thank you, Zakaria, for the presentation. I'm curious more about the data because you showed that in quantum SVM, it did not perform in comparison with other classical. So one of the reason maybe is the data is not topological. So quantum can be used mainly in machine learning where the data is topological, which means that too many features but less depth in the data. And this is one of the reasons. Can you elaborate on this, or maybe you have another opinion why quantum is not, it's promising, but it did not show the expected results?
Yes, yes, we noticed that. We think that's because of the the qubits, because we only use 4 qubits to, as everyone knows that the data set contain over than 700 features, so we reduce those features to with the feature selection to 100, and after that we choose only 4 features. So probably this is the lack of information.
So what approach did you use to reduce it? PCA or you have
Yes,
some
PCA. Yeah, we know
PCA?
we used principal component analysis.
PCA. And was there any reason why you have chosen 4 qubits?
I don't have, to be honest. We don't have.
Why not 5, for example?
Yeah, well, I chose 4 and 5. 5 didn't perform well, so give us lower accuracy. So we stuck on 4. So we didn't have much time to work on a higher number of qubits. This is the problem.
Okay, another follow-up question.
Yes.
Last one. I guess so.
Yeah.
So, have you tried the optimization, the transpiler function to optimize how the qubit? What was the depth of your circuit?
The depth previously we were being used in for 2 layers, and after that we tested the 4 layers, but there is nothing showing up as a impressive results. So we just focused on quantum supervector machine with only 1 layer.
Okay, thank you.
Thank you so much.
Assalamu alaikum. Thank you so much, Zakaria, for the great presentation. You have a straightforward question, which is why did you choose poly feature map for the feature map in the QSVM?
Yes, it's not arbitrary choose. We tested before, like angle encoding. It didn't give us a good results. After that, we tested double Z feature map. We didn't reach what we are looking for. We tested also amplitude encoding, and after all, the best encoding method was Pauli feature map.
And what was your metric when you say best encoding? So that would be really interesting to see a slide with the comparison between the different encoding methods, and then what was the benefit, and then why you choose poly feature map for the encoding.
The metrics were especially in the code, so we didn't mention there here. So I put them only in the code. So that's why we are based on it. Just to be clear, we get based on that, on the term of the accuracy of training and testing, the F1 score and the recall, also the ROC. So that's why we choose this this
Not
encoding.
the complexity when you deal with the data sets, or the time of the training, for example.
We didn't focus, to be honest, we didn't focus on the timing, because we just ran the code. And speaking about complexity, here probably it's not, or we can say that the complexity will not take a huge part, because we are not using a deep circuit or something like that. That's why.
Okay, thank you. Thank you so much.
Thank you so much.
Any other question?
Thanks, Dr. Zakaria, for your work. So yeah, so I mean, maybe, yeah, I think you had a chance to use many qubits, right? So I think it's pity that you didn't go for more than 4. Yeah, because yeah, but anyway, but at least did you include? It seemed that you used simulation, right?
We use
Yeah.
simulator.
Yeah. So did you
Yes.
include noise in your simulation?
Yes, because we use shorts around 1000, so we include the simulator, the noise.
No, no, no. I mean, did you use some noise? Didn't you use some noise model to your
No,
simulation?
no, I didn't add it. No.
Okay. So did you experience or experiment with the number of layers in your variational circuit here?
I didn't hear you well.
So number of layers, I think this QSVM probably is parameterized with number of parameters or layers you have. So did you try to tweak this parameter and see how things goes?
We tried like several times. So the best configuration, as I mentioned before, is this one. So if we had too much time, probably we will reach something better.
Okay. Thank you very much.
Thank you.
Any more questions? Okay, Zakaria, you are from Jordan, right?
No, from Morocco.
From Morocco. Okay, we have Zakaria, so we have also Arab brothers from who is participating with us in the hackathon online. Any more questions? Okay, I think that's maybe enough. So thanks, Zakaria, for the nice work and nice presentation. Big applause for Zakaria. Okay, and now we are ready to move to the next team.
Team 10.
Team 10 is coming while Team 10 is is preparing. We just leave this time for our jury members to give the grades. Okay, Team 10. So Nasser,
Hello.
where are you from?
Hi, we're Team 10. We are from Jordan.
Okay, so what are your colleagues? فين زمايلك?
Yeah, my colleagues are
Okay, can you open all of you? Can you open your camera, please?
Not all of us can. And only 3 of us will be presenting for the sake of time management. But all of us worked and contributed to the submission.
Okay, then can you define and say your names in the beginnings for the record so we can keep track of who's with us in the session?
Okay, my name is Rama Bashad.
And I am Nasser Elbis.
I am Yusuf Rihani.
Okay,
And I am Kinda Mashal.
okay, that's great. So you are 4 now participating online.
No,
We have 2 more.
also in the team.
Okay.
My name is Noor Abu Ghazali.
Can you say your name again, please?
Noor Abu Ghazali.
Okay, thanks, Noor. Those
And
else?
we also have Khalid, but his mic is not working. Khalid Abu Qtesh.
Okay. Okay, welcome team 10 and also team 10 from Jordan. Big applause to them. They are brave people. They are participating online and trying to working in the same pace and with the same speed with us as offline colleagues here. Okay, shall we start? Is the counter
Yes.
ready? Okay, so please start. The
All
floor
right.
is yours.
Hello, everybody. So today we decided to work on the Parkinson's disease classification problem. As our team is from a data science background, we aim to apply machine learning algorithms using quantum technology to a highly dimensional dataset with significant feature correlation. Meeting the challenge of quantum computing requires developing an understanding and knowledge of the science of quantum mechanics and its underlying theories. True or negatives, the data represented a key challenge, a severe class imbalance with disproportionality, low number of individuals, the negative class, compared to a healthy individuals, which is the positive class. In order to address this, one of our primary objectives was to maximize specificity. It's a metric that measures the model's ability to correctly identify ill individuals. So here, the true negatives are the number of individuals who actually have Parkinson's disease and were correctly predicted by the model as having Parkinson's disease. The false positives are the number of individuals who have Parkinson's disease, but were incorrectly predicted by the model as healthy. So we went into machine learning with the imbalanced data. As you can see, one of the main obstacles we faced was this imbalance. The number of individuals in negative class were significantly lower than the number in the positive class. We decided to tackle this problem using multiple feature selection methods, with the primary on the specificity. We started with selective PCA. We basically identified subgroups within the dataset features that were extracted using a specific feature analysis of sound or another. And then we conducted what we called selective PCA. This gave us the accuracy of 77%. Then we decided to go with the normal thing, which is the dataset-wide PCA. The number of primal components retained were determined by a threshold of 94% cumulative explained variance. This gave us the accuracy of 92. All of this were tested using an SVM model. We'll get to that in a little bit. Our third feature selection method was iterative leave one out. We basically eliminated iteratively a lot so basically we made an iterative process on an SVM model on a full feature set. We ranked and removed the 3 features that contributed most to the highest specificity. This gave us an accuracy of 77%. The last method we used was the random forest. It mitigates overfitting and enhances accuracy through 2 randomization techniques. We used 2 models, the 30 feature and the 60 feature. The 30 feature was the 96th percentile with accuracy of 85, and the 64th feature with 91 from the 91.6th percentile with a threshold of 80 accuracy. However, accuracy isn't the only important metric. This is a medical classification, and we need high specificity. And so we looked for the specificity percentages. As you can see, the best one was the leave one out method. The top 3 were leave one out method, random forest 64 feature, and a dataset-wide PCA. Now we're gonna go to the classification with Yusuf.
Okay. So for the classification problems, we tackled the problem with multiple models, including XGBoost, CatBoost, logistic regression, and SVM. While all models somewhat performed similarly pretty well, SVM seemed to be the best of them, providing us with a 0.92 F1 and 0.92 accuracy out of 1. So how the way support vector machines work is that they were able to the reason we use support vector machines is that they're helpful for handling high dimensional data, and they have a solid theoretical foundation, which is one of the main reasons we chose them, as well as that they have a quantum counterpart, since we noticed that there aren't many quantum models available right now. So for the quantum ML integration, for starters, we did quantum feature encoding. 2 of the main embedding techniques we looked at are angular encoding and amplitude encoding. Angular encoding obviously mapped every feature to a single qubit, while amplitude encoding mapped them to every qubit mapped to around log m by n qubits. Every qubit mapped log m by n features, which ultimately was one of the reasons we chose amplitude encoding, because angular encoding would be helpful if the dataset had a small number of features, which is not present here. The dataset here has around 750, which is very high, which is the reason we chose amplitude encoding. So the number of qubits we settled at was 6 qubits to represent the 64 features present in our dataset. And for the reason why we used what we used, I will pass it on further to Khalid. I think Khalid or Kinda.
Oh, that would be me. Sorry.
Oh yeah.
Okay, so we were discussing the feature embedding techniques that we were working with. We did look at multiple different feature embedding techniques, including basis encoding, amplitude encoding, and Hamiltonian simulation, including two ways, something called the Ising way and the Hamiltonian simulation. So what we opted for was this data already has 750 features, and there was a lot to describe within the data. And we were having some problems because we had imbalanced classes, so less information would make us prone to more errors. So what our approach was, pick an encoding that encapsulates the biggest number of qubits, which is like if we went with 6 qubits because we were told that our like limits of qubits should be realistic, should be around 5 to 6, and for the time frame of running the model. So we went with that number and we went with amplitude encoding, which gave us 2 to the 6 features, equaling to 64 features. So that's the number of features we ended up working with. And we spent most of the time actually tuning the classical models, in hoping that getting a really good working classical model will yield us a great quantum model once we transform it, which didn't turn out to be the case, but I'll keep going. So we were torn between using Qiskit and Penny Lane, and since we ultimately wanted to run on IBM hardware for the QPU testing, we chose to go with Qiskit for stars. But then we faced lots of problems. It was poorly documented. Lots of the libraries were and the functions were deprecated. Lots of the tutorials that were online, especially that were new to the field, gave us trouble. So we ended up going with Penny Lane instead, and that was a much smoother experience. We tried implementing multiple different models. We compared lots of different models for the classical. Even when we did support vector machine, we did lots of pre-processing. We did scaling. We did PC principal component analysis. We also performed hyperparameter optimization using this library called Octuna, which is really neat. You guys should check it out. But we used it to get we made like 3 splits for validation and for testing, so we can
Thank you. Thank you. Time's out. Okay. Any question? Hello everyone. Thank you so much for this great presentation. I just want to point out something. Well, it's more of a remark than question. So at the beginning you chose SVM because it was better performing on the data set because you compare different like classical models and then you said like SVM is the best for the classical model. Let's create a version of QSVM and try it on this data set. I just want to flag out that this approach doesn't work all the time. So that would be really interesting to see the 4 like classical models or the 5 classical models that you presented, implementing like 2 of them on the quantum hardware and see the comparison and not just select the best on the classical and implement it on the quantum.
Absolutely. And this was something that we realized while we were working. So we actually have allocated most of our time to getting the best classical model, thinking we can simply convert it to a quantum model. And part of the reason we went with a support vector machine is that it is one of the easier models to convert to a quantum state. So we wanted to compare apples to apples. We didn't wanted to compare an SVM with like a logistic regression for the classical. And as you can see, there's a big split in actually the accuracy and the metrics that we got from the quantum model. And turns out these hyperparameters and the data processing does not translate, simply for a couple of reasons, mainly because feature embedding transforms data in a different way. Quantum kernels inherently interpret the data in a very different way than what we use with regular RBF kernels. And also one of the things that we noticed after reading more about the subject, trying to examine why our results were so far off from the classical, was that amplitude encoding in itself is a bit of an emerging technique that has troubles with preparing the vector that has a norm of 1, and reading out of it is also still an ongoing challenge. So amplitude encoding in itself is not that stable of a technique, which also yielded us to having less representative features when we trained the model.
Thank you so much for this beautiful answer. I would say you should explore quantum reservoirs. You'll find it really interesting, like if you want to explore this thing more.
Yeah.
Thank you so
Thank you.
much. Yeah.
Thank you. Yeah, thank you for presentation and work. So, did you include noise? Is this results on actual quantum backend or simulation?
We did actually, and in the testing, we included 2 pipelines, one with the noise in the pipeline and one without. The results shared in the presentation are the ones that are not noised, but we have pushed the code that does the noising on GitHub. But we simply ran out of time trying to evaluate the metrics, as adding the noise
Which
resulted
noise
in
model
a lot.
did you use? Which noise model did you use?
I believe it was Rihani.
I think we used depolarizing channels.
Okay, and what parameter did you use for that?
Depolarizing.
We used 1% probability. Obviously, that's the base probability. We could change it as we have the way set it up, but the default is 1%.
Okay, last question. Did you use backpropagation in your training on Penny Lane? Okay, well, doesn't matter.
No, we did when we were experimenting with quantum neural networks.
Okay, thank you.
Sorry.
Thank you. Team number 10 from John.
But we ended up
Thank
going
you.
with quantum SVM.
Thank you. Thank you. Thank you. Now let us have some time for the judge. Until this team 8 is ready. Team 8.
Yes.
Okay. Can you please open the camera? You have any colleague? Or only you?
Yes, there's Hamza and Najib.
Okay. Okay. Are you ready to start? Oh, can you present yourself first? Oh.
Yes, of course. My name is Hadi Mouzayi and I'm a computer science student from Algeria.
Algeria, yes. And the others?
I'm a PhD student in theoretical physics from Algeria also.
Yes. Anyone else? Okay, you can start from now. Good luck.
Okay, thank you. Hello everyone, I hope you are all doing well. Today we are going to present our solution for the smart traffic optimization in the new capital. Our team consists of Nada Aiken, our mentor, Salmi Mohammed Najib, Ben Qaddour Hamza, and me, Maidil. Ambulance delays is a public health crisis. Why? Because apparently there's 20% of emergency deaths attributed to the traffic delays of ambulances. Thus, we present our solution Cortex to solve this problem. Our problem adheres to 4 of the UNESCO SDG goals, which are the health and well-being, the industry, innovation, infrastructure, sustainable and communities, and climate change. The problem that was presented to us is that there is one ambulance that must transport 5 patients to a hospital. Our goal is to minimize the total travel distance with the constraints that the ambulance can make different trips. Each trip has a maximum of 3 patients, and all the patients should attend the hospital. For the pre-processing and mathematical setup, we got the JSON data that contains the hospital and patient's locations using GPS, and we calculated the distances between each points. Then we did mathematical formulation for both classical and quantum algorithms. For the first, we used classical approach. We used a simple brute force approach where we grouped patients into 2 trips, which is a combinatorial grouping. Then in each trip, there is different permutations of patients. And we sum the total cost across these groups or trips and choose the minimum travel distance. Our solution is trackable and gave us the global optimum, which is shown in the optimal travel distance here, and was executed in 0.004 seconds. This method is exact for the scale, but when the patient's number is bigger, it became not very optimal to use. And this graph shows the optimal route for our solution. Now Hamza will present the quantum approach that we used.
For the quantum approach, we have used the QAOA algorithm. So we start by transform our problem to QUBO formulation. After that, we create ansatz and try to transform the QUBO formulation also, or do the mapping to quantum Hamiltonian. Then we try to optimize the parameter of the quantum circuit until we got the optimal parameter. Next slide. After we got the optimal parameter, we try to do samples using sampler. After that, we get the bit string, and we take the better bit string that give us the decoding of the trips. So we take the better one, and for the first 5 qubits, it showed the first trip, and the 5 other qubits, it gives the second trip. Next slide. Yes, this is for the optimization part. And after that, we get the parameter, optimal parameter. And after do the samplers, we try to take the optimal one that gives the solution. Conclusion: both classical and quantum approach give the same result, but sometimes the quantum approach give a wrong result due to noise. And in order to optimize this noise, we can use quantum error mitigation for a better result. Thank you.
Okay, thanks very much for the nice presentation, nice work, and indeed you finished before the time, so you might have more questions. Yeah.
Yes, thank you. So the other teams working on the same problem have found that the optimal distance about 57 kilometers, while you found like 23 kilometers. So this is a little bit weird for me. Can you comment on that, please?
Yeah, for the classical approach, we only use 2 trips and group the patients into these 2 trips, and then calculated the possible permutations in each one and summed the result of them. So that was our solution.
Okay, any more questions?
I think you used the distance of the line of sight, for example. Did you use the real distance of the pathways between these locations to reach this result, 23 kilometers? or is it just the line of sight distance?
What do you mean by real distance?
I mean just by calculating a distance between two GPS coordinates of two positions. Did you use just the GPS coordinates without considering the routes, the real routes on the map?
Well, we used the GPS coordinates and calculated the distance using the Haversine formula.
This is the reason. Okay, thank you. As a question?
Okay, any more questions?
So thank you so much for this great presentation. The results are impressive actually compared to what we saw from the other teams. I just wanted to know like why you stick to QAUA for the quantum approach. Why haven't you tried, for example, Cubo plus annealing, like quantum annealing? Have you heard my question, Hadi?
Yes, basically we don't use quantum annealing anymore. We don't have too much time. That's why we follow the algorithm.
All right. Thank you. Thank you so much.
Yeah, thank you, Hadil and the team. I have a question about the depth of the circuit. So when you implemented the quantum circuit, how many gates did you end up with, and how big was your circuit? And have you had a chance to optimize it using the transpilation function in Qiskit?
Basically, we have used the air simulator, so there is no transpilation. Yeah. So we don't basically we can't optimize or transpile the circuit because we use the simulator. We don't use a backend or fake backend.
Okay. So
Yes.
can you just remind me of how many qubits you use when you reduce the
10
features?
qubits.
10.
Yes. 5 for chip 1 and 5 for chip 2.
Okay. Thank you.
Any more questions? Okay, if not, we thank Team 8 for the nice and impressive work.
Thank you.
And with that, we would like to conclude the session, the presentation session, and we invite all jury members to go to the deliberation room to finalize the grading of the teams. After, of course, they finish putting the marks.